In the last lecture, we learned the perceptron algorithm, which is an algorithm to find a separating hyperplane between two sets of points which are which are given to be linearly separable. Okay, but many of you would have already guessed that not all data points are such that the good and the bad points will be separated by a line, right? It's kind of quite over optimistic to expect that in all the problems that you give, the good and the bad will always be separated by a straight line. In fact, there are very, very simple good bad configurations for which this perceptron kind of, or a linear separating hyperplane may not exist, and hence the perceptron algorithm will not work, right? So if you think about this simple example here of 4 points in this kind of a configuration, you can easily see that there is no single line that separates the blue from the green, right? And in fact, this is a very common example suggested, and it is usually referred to by calling it the XOR function, right? So if you think of 0, 1, 0, 1, then the blue points correspond to those coordinates where the XOR of x1 is 1, right? So if x1 XOR x2 is equal to 1, then it is blue, and if it is 0, then it is green. So you generally say that the perceptron cannot learn the XOR function, okay, because it's in some sense a smallest example for which this is not possible. But now, does that mean perceptrons are very limited in use? No. What it means is that you just think of perceptron as a single building block, and you can now make much more complex separations using multiple perceptrons, right? So for example, in this case also, it is very easy to see that if you are given two perceptrons, maybe you will find these two hyperplanes, and then you will kind of take a logical condition, right? I know if it is below the top hyperplane and above the bottom hyperplane, then the point is blue, otherwise it is green, right? So these are called when you use multiple perceptrons, right, you call it multi-perceptron, and sometimes you call these as neural networks. Okay, when you have a collection of perceptrons, you call them as neural networks. So using this logical conditions on top of a collection of perceptrons, you will still be limited to things that can be separated by lines like this, right? You may still be limited to these kind of separation where the good and the bad will have to be separated by piecewise linear kind of curves, right? But what has turned out to be more common, a success story of perceptrons, in fact, are when you have a multi-layer perceptron, right? So you have a collection of perceptrons in one layer. You remember that we said this inner product with the normal to the hyperplane, you can model it as a weighted sum done by a very small neuron. Now in the second layer, you have extra neurons, and the output of these are wired to this, right? So this is a double layer neural network or a 2-layer neural network, and in general you have multi-layer neural networks, and these multi-layer neural networks are extremely powerful machines. They have been practically very successful, and they can learn very complex separating surfaces much beyond the task of a single, much beyond just a linear separator, right? And when you have a lot of such layers, you generally call them the deep neural networks, and they have been a phenomenal success in the recent times. But you should know that for a single perceptron, actually kind of learning or writing an algorithm to find out that hyperplane was easy. Here that algorithm needs to be adapted. You have something called backpropagation learning and so on to find out the weights for such a multi-layer neural network, which will do the required separation. But that is not the topic for today's discussion. The topic for today's discussion is to extend this linear separators to nonlinear separator by what we will call as by finding an embedding in a higher dimensional space. Okay, so let's this is going to be the focus of our lecture today. So let me begin by a small example. Okay, so suppose your good points, right, and bad points are not separated by a linear separator as earlier, but instead let us say they are separated by a circle. Okay, so the good points, the bad blue points are inside, and let's say the good green points are now sitting outside this circle. Okay, now this is a separation task that is beyond the capacity of a perceptron, right, of a single perceptron for sure, because there is no straight line which separates these 2 points. Okay, for just since it's a starting toy example, let me even simplify the problem by assuming that the center of this circle is in fact the origin of the plane in which this data is represented, so that our next steps become easier. Okay, so here you really cannot separate this using a linear combination. So if this is the x1 axis and this is the x2 axis, your inner product of some a with x, right, which is some alpha x1 or a1 x1 plus a2 x2 kind of thing, will not work. But what will work is if you could make a decision based on x1 square plus x2 square, right? Because we know that if this circle had a radius r, then if x1 squared plus x2 squared was less than r, points are blue, and if the x1 squared plus x2 squared is more than r, the points are green. Okay, now but how do we now but we somehow still want to use a linear separator, but maybe in a higher dimensional space. So what we do is we pick what is known as an embedding function. Okay, an embedding function, let's call it phi, from the actual the vector space in which the data resides, which is Rn, to a higher dimensional space. Okay, R capital. In the example that we are having here, we'll just use phi of xy to be x comma y comma x squared. Okay, let me use x1 x2. Okay, so phi of x1 comma x2 is x1 x2 x1 squared plus x2 squared. So your phi is essentially in this particular case a mapping from R2 to R3. Okay, now if you see, let us plot all the same data points in R3. Okay, so how will that look like? Maybe it's slightly, since it's a three-dimensional picture, I want you to rather imagine. My drawing won't be able to easily catch up with your imagination. So this is your x1, this is your x2, and this let me call as x3. That is your vertical axis, right? This is nothing but x1 squared plus x2 squared, right? Now what do you see, like for every green point, every blue point, now you project it into, or you embed it in R3 using this function phi. What do you get? What you can observe is that if I take the z equal to r squared point, right, and then imagine okay, my drawing again may be bad. Imagine a hyperplane, right? This is a plane. Since it's in 3 dimension, I can just call it a plane which is parallel to the x1 and x2 axis. So if I call x1 and x2 on the horizontal plane and x3 as the vertical, then this is a horizontal plane which is lifted above the x1 x2 plane by an intercept of r squared, right, with z intercept or x3 intercept equal to r squared. Okay, this is the plane that I'm talking about, right? Now, what is special about this plane? I claim that this is a separating hyperplane for the data in r cube. Why? Because if you see all the blue points are going to lie below this plane, because their x1 squared plus x2 squared value is less than r squared, and all the green points are going to lie above this plane. Right now, if I draw it, it might look cluttered. Actually, I should have just probably drawn the I should have just drawn the x3 axis, and then it would have been clearer, right? So if I just drew the x3 axis, and so let's say this is 0, this is r squared, all your blue points are going to be below this plane, and all your green points are going to be above this axis, right? So what you have is a linear separator. Okay, listen, it's a linear separator after you do the embedding, right? So we are saying that G and B can be separated by a linear separator in R3, right? Or more correctly, I should say the phi images, okay, the phi images of G and B can be separated by a linear separator in R3. Okay, so this is the embedding trick. Okay, now what is the first question here? Like, how did we identify this third coordinate to be x1 squared plus x2 squared? We looked at this picture, and from our intuition we understood that okay, this is a good choice. But human beings can do this up to maximum of 3 dimensions, right? What if your data is in a million dimensional space, right? Who is going to tell you what circle is the best, or whether it's a circle, or is it an ellipse, or is it or is it like a torus? What kind of shape will actually separate this, right? So that question we would like these surfaces to be kind of decided automatically by a program. Okay, as a pedagogical starting example, this circle is good. But in general, when you have a massive data set, massive high dimensional data set, what do we do? Okay, so there again, the technique is to kind of project it into a very high dimensional space, so that a lot of separators become available to us. Again, let me try to explain it with an example, right? So let me to begin with, as a starting example, let me say that originally the data lived in a single dimensional space, right? So it is something like the data is concentrated on a real line. So maybe there are some green points, right? And there may be some blue points on a line. Okay, so your initial data is separated, is on a line like this, and it's clearly not linearly separable. Okay, now what phi I will choose is, now I can write just phi as phi of x. I'll choose it as 1x x squared all the way to some x power d for dimension. Okay, d for degree in this way, right? So now if I choose this phi of x, right, how is a separating hyperplane in, okay, now what is this dimension? This will now be a vector in r d plus 1. Okay, so this n here is equal to d plus 1. So how will this vector in r d separating hyperplane in r d plus 1 look like? Like, it will be defined by some a0 a1 to ad, right? And your decision boundary, since it's a hyperplane, will be essentially checking whether a0 plus a1x plus a2x squared plus etc. ad x to the power d is less than 0 or greater than 0. Okay, let's still stick with the model where it is less than 0 and greater than 0, as opposed to less than b and greater than b. Anyway, here we have this 1, it would be automatically handled. Okay, but now this object looks familiar to you, right? We all know these objects as a polynomial. Okay, so viewed back in the original one-dimensional space, what this condition here is checking is you are kind of plotting this polynomial and checking whether your point, when you substitute it into the polynomial, when the x value you substitute it into this polynomial, is it less than 0 or greater than 0? Okay, so in some sense, though we have a linear separator in Rd plus 1, you have a polynomial separator in R. Okay, so you can afford to have something like this kind of a separators, right? So even though you have only a or maybe like, this polynomial would be like, since you have 1, 2, 3, 4, 5 zeros, this may be a 5th degree polynomial. So by doing this phi, what you automatically get is like you have at your disposal, you have at your disposal all polynomials of degree at most d as potential separators. Okay, so for example, you really do not need to worry whether the circle was centered at origin, right? Even if it was centered somewhere else, then the more appropriate metric would have been some x1 minus that center's first coordinate, the whole squared, minus x2 minus c2 squared, but this will still be a second degree polynomial, and then that will be available to you if you choose this as your phi. Okay, so rather than fixing on a particular function, you pick your kernel so that using this kernel, the hyperplanes in that higher dimensional space will correspond to a rich class of functions in the lower dimensional space. So here the hyperplanes in this d plus 1 dimensional space will correspond to all polynomial separators of degree at most d. Okay, but now I intentionally chose a toy example where your input was in one dimension because I was not sure how many of you will be already familiar with or comfortable with multivariable polynomials, right? But they are no big deal, right? I mean, instead of this, you can actually have, let us say, if you wanted something like an r squared to large n embedding in terms of polynomial, what would you choose as your, let's say, phi of x1, x2? So these three will form the degree 1. These three can span all degree 1 2 variable polynomials where the variables are x1 and x2. If you, in addition, if you want to span all the degree 2 polynomials, you will have to also include x1 squared, x2 squared and x1, x2. Okay, this will include all these 6 guys can together span all the up to degree 2, I mean degree 0, degree 1 and degree 2 polynomials in this, right? But what we are writing here are monomials in the sense that you haven't added 2 terms together, and these are monomials with the constant coefficient being 1. These are sometimes referred to as monic monomials. Okay, if you wanted 3 dimensions, all degree 3 or lesser polynomials, you will have to add x1 cube, x2 cube, x1 squared x2, x1 x2 squared. That's it, right? You will have to add these also. So your n in this case will become 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I leave it as an exercise to check what will be n if you are mapping from what will be n for some given n and d, right? Or equivalently, this is the number of monic monomials in n variables with degree at most d. Okay, this is an exercise question. I'll give you maybe the answer also. This turns out to be n plus d choose d. But okay, that's an exercise. Those who are in my discrete math, those who are TAing for my discrete math course will have an advantage here on solving this exercise. Okay, so yeah, so that is how we pick. This is one very good choice of an embedding where you essentially pick all the monic monomials up to some degree. All right. So, now let us still, we have found this embedding and we said that, okay, they are separated by this, but can we still run this perceptron algorithm together with this embedding? Why not, right? So let me see if I can rewrite the perceptron algorithm here. So the perceptron learning algorithm together with embedding. Okay, so in this case, what will be the inputs to the algorithm? Okay, as always, you need this good set and the bad set. Okay, so a good set, okay, let me label them as x1, x2 to some xk, xk1, k points. Okay, and then the bad set will be some, I'm just having a consecutive number which I'll need later. As of now, you don't need to bother why I'm calling it by these numbers. Okay, so this is a subset of Rn, this is another subset of Rn, this is the good set, this is the bad set, right? Sorry. Okay, this is the good green. Now this is the good green set versus the bad set. Okay, sorry for the pen confusion. But in addition, what else do you need? Now you also need this embedding function from your Rn to some higher dimensional space R capital N. Okay, so in general, this N capital N would be much bigger than the small n. Okay, it doesn't matter. Now, what is the output that you are expecting? Okay, so output what you are expecting is some A in R big N. Okay, so this is important. A in this R big N such that for all good x, right? Since I have named them, for all xj in the good set, you have axj to be greater than 0, and for all, okay, sorry. Since we are running, since we are running this in the higher dimensional space, it will be phi of xj, right, greater than 0. I mean, don't bother about the subscript j, since I just indexed the points for another reason which I'll tell you later. That's why you have this j. For now, you can just say for all good points x, inner product of a with the embedding of x has to be positive, and for all bad points, the inner product of a with the embedding of x has to be negative. Okay, this is what we require. We need an a in Rn which satisfies this condition, right? Now the algorithm should be simple, right? The same thing, I'm just rewriting what we did earlier. Repeat until there is no update to A. Yeah, but before that I should start with initializing A is equal to 0, 0, n in the cap. So A is a capital N length vector, okay? And then what do we do for each xj which is good, for each xj good, if it is wrongly classified, right? If a inner product with phi of xj is less than 0, which means it violates our requirement, right? So it violates this condition. Let me call it as these two conditions. Let me call it as star. If it violates star, then what do? We update the weight vector. We will say a is now equal to a plus phi of xj. Right? Remember, we have to update a with the phi of xj because a is a capital N dimensional vector. And for each xj in the bad set, the condition is also different. You check if a phi of xj is greater than 0 this time. That is when it will violate the star. And in this case, your update rule is also minus, right? Remember that this is a minus here. This is this. Okay. Now, This is true, and then we know that if at okay, when do we know that this algorithm will terminate? This will terminate if these sets, right? Phi of x such that x is in G, and so let me call it as phi G, and phi B, which is phi of x, x is in B, are linearly separable in R n, right? That is when this will terminate, and in that case we also know how to in fact bound the number of steps of this algorithm. Okay, so this way we can essentially just run the perceptron algorithm in Rn, okay, in R capital N, and get the result. Okay. There is only one catch to it, okay, and that catch is more of a computational issue, right? So to get a very rich class of linear separators, you may end up needing a very big value for this capital N. Okay, you may have to go to a very high dimension, in which case all these calculations, all these inner product calculation scale up with capital N. Right, because to compute an inner product in n dimensions, you will need n multiplications. So this is a computationally costly thing if your this ambient space or this hidden space dimension, this capital N, is very large. Okay. Now what is possible is that we can actually kind of modify this algorithm using what is very fondly known as a kernel trick. Okay, and this will save us a lot of computation in many cases. Okay, so there are two key observations to this kernel trick. Okay, there are two key observations that we have to make. Okay, so the first observation is that if you see most of the operation between the vectors, okay, so let me use a different color for the observe, right? So if you see most of the, okay, this is anyway the output guarantee, we don't have to worry. Most of the computations that you do in the algorithm are inner products. Okay, now what is this is an inner product in a capital N dimensional space, I agree, but if you could, at the end of the day, you are only getting one real number. After doing this n multiplication, you are adding them up all and just getting one number. Okay, so the observation one is that most computations are inner products, right? But unfortunately, directly they are not inner products between two embeddings, right? So why am I saying that? So suppose I wanted to, that's the second observation, let's say most computations are inner products of the form A phi of x. Okay, so let me say that full, right? So this phi of one of them is phi of x, but this A is not, at least we don't know whether A is phi of some other vector from the smaller dimensional space. Why? Because A started off as the 0 vector and A was kind of, added in, kind of got updated in this, right? By the way, this doesn't mean, when you do this kind of an operation, it is not the case that this A is of the form some phi of A prime, and this A prime can be obtained by just adding this plus xj in this case or minus xj in this case, right? What I'm trying to say is that this phi is not a linear map. In fact, that is why you get a nonlinear separator. A is not a linear map. So whatever you are doing to A, all the operations that you are doing to A are linear operations in terms of either adding an embedding or subtracting an embedding, but it needn't correspond to linear operators in the smaller dimensional space. Okay. So this is the first observation. Most computations are of this form, right? And observation 2 is that your A is a linear combination of what? I want you to guess, of phi of xi, where xi is in G union B, right? Why do I say that A, this norm of the separating hyperplane, is a linear combination of the embeddings of xi? That's because you start with A equal to 0, and then at each step either you add one of these embedding points phi xj or you subtract them, right? So in fact it is more than a linear combination. What is it actually? It is an integer linear combination, right? Why? Because this A is always going to be something of the form sigma j is equal to 1 to, I think we had L points in total, right? Or let me, in the form some alpha j phi of xj, right? So what is alpha j, by the way? Like if xj is a point in the good set, if xj is a point in the good set, then alpha j is the number of times xj caused an update. Because every time xj causes an update, you keep adding the same phi of xj, right? So this alpha j here will be number of times xj caused an update for a good point xj. If xj was a bad point, then minus alpha is the number of times you got that update, right? If xj was a bad point, then alpha j would be negative, and the magnitude of that will be the number of times xj formed an update. So if an xj never updated your A vector, then alpha j will be 0, whether it is a good point or a bad point, okay? So this is the second key observation, okay? So the first observation is that most of your computations are of the form A phi of xj, and the second observation is that this A is it's an integer combination, but we will only need the fact that it is a linear combination of the embeddings of the points, right? Now, combining observation 1 and observation 2, this is the soul of the kernel trick, okay? If you combine observation 1 plus observation 2, you can write this inner product of A with some phi of x, right, as what is A now? A is sigma j equal to 1 to L, the number of points, alpha j phi of xj, inner product with phi of x. Okay, so I have just, what have I done? I have replaced this A with this guy based on observation 2. Okay, but now this is an inner product. What you see here is an inner product, maybe in Rn, but it is still an inner product, and inner product obeys linearity, right? So this is equal to sigma j equal to 1 to n alpha j, inner product of phi of xj, phi of x. Okay. So this is the result of combining observation 1 and observation 2. What is the result? You can say that all the computations are of the form some sigma over I j equal to 1 to L alpha j phi of inner product phi of xj. By the way, this x is also a point from we only use it in this condition. This x is also an element of G union B, right? So maybe in that sense, let me call it xi, okay, just to make it different from j. So phi of xi, where xi and xj are the points in the data sets. Maybe good, maybe bad, right? They are just points in the data set. So they are members of G union B. Okay. So this is the combination of observation 1 and observation 2. What does it help? How does it help in terms of computation? What it tells you is that you should, if you have, can we compute, or the question we should ask is, can we compute phi of xj, phi of xi efficiently. Okay, by efficiently, what do I mean? I can compute phi of x and I can compute phi of xj and I can compute phi of xi, and then the inner product will take capital N time, right? But what I want is to do it in a much more faster way. Probably, by efficiently, I mean in time or steps independent of this capital N. Okay, looks surprising in the beginning, but the big advantage, suppose you could do this, you could do this, then you really don't have to worry about into what high dimension space you want to embed. You can make your N as large as possible. You can even make N actually infinite. Okay, you can even do this embedding into infinite space, provided this computation can be done in number of steps that is independent of N. Okay. So before giving you the formal details, let us take the simple kernel that we already, one of the simple kernels that we studied, right? We did it from RD to RD plus 1, where phi of x was mapped to 1 comma x squared all the way up to x power d, right? So in this case, how would the inner product between two vectors after their embedding look like? Phi of x comma phi of y. Let me just write phi of y also here. That will be 1 y squared all the way up to y power d. Now what is the inner product of these two vectors? It is 1 plus xy plus x squared plus y squared all the way up to x power d y power d. Now, if you look at it this way, we haven't saved anything, right? We are still doing d plus 1 multiplications, right? But we know, if you stare at it for a moment, many of you would have already observed that this is a geometric progression with common ratio xy, right? So I can actually compute this as 1 minus xy to the power d plus 1 by 1 minus xy. So suddenly you don't have to do d plus 1 multiplications anymore, right? You just have to do an xy and then this exponentiation, which in a floating point computation, it is easy to do, right? So suddenly this computation, right? This is, the computation time is independent of capital N, or in this case d plus 1 is equal to the capital N, is independent of capital N, right? So you only need to compute this phi x comma phi y, and you can even, actually the observation says that you only need them for where both x and y are data points. So you can even just compute them as a matrix a priori and keep it, right? And then just substitute it whenever you are asked for it, right? So what do I mean whenever you are asked for it? So all these calculations, you will have to rewrite it that way, right? So let me copy this somewhere and then, how do I say, right? Erase this and change it to the new algorithm. Okay. So I have copy pasted the old perceptron learning algorithm into a fresh page. And now we will say, it is still with embedding, but we will never do this embedding directly. Instead, we will just use the kernel trick. Okay, we will just use the kernel trick, right? This input is now again this good points x1 to xk and the bad points xk plus 1 to xl. So there are L points if you count g and b together. And you won't be given this embedding function phi. Instead, what you will be given is this kernel k, which is actually a function from Rn cross Rn to the real numbers R, right? And what is the assumption? The implicit assumption is that this k of some x comma y should be inner product of phi x and phi y, but this is all hidden, right? You really do not even say that there is a, you don't even need to technically know which is the embedding function phi. All you care is that k should be expressible as the inner product of the embedded versions of 2 points, right? So as long as k is of this form, we only need to know k. We don't need to know what is phi. Okay, and what is the output now? Again, for the good points you want greater than 0, and the bad points you want less than 0. But there is no point in giving us an a, right? Because if you give us an a, we still need to take an inner product with phi of xj. But our point is not to compute phi of xj. So what we want is not this a, but what we want is this coefficients alpha 1, alpha 2 all the way up to alpha. In fact, they will be integers. So let me write it as integers to the power L, right? So this is what we want to know. So in each update in the perceptron algorithm, we should keep track of whether we are adding that xj or phi of xj or subtracting that phi of xj, right? So we will not have this a directly. Again, if I make my margin note here, finally what would be my a be? A will be just sigma of alpha j xj, j is equal to 1 to capital L. So remember, when I write j equal to 1 to L, it runs over both the good points and the bad points. This is just a dirty trick with notations to not write, the summation as two pieces, once over the good and once over the bad. That's why I thought of having a running index from 1 to L together for the good and bad points. Okay, so we don't have an a directly, but once you have alpha 1, alpha 2, alpha L, by the way, this is wrong. This is not xj, this is phi of xj. If you are ready to embed, then you know what is the a vector, which is nothing but this alpha linear combination of the embeddings, right? So this is what we had seen here, if you remember, right? This is our a, right? I'm talking about observation 2. Okay, let's come back here. Now, again, you cannot really compute this inner product directly using a. So you will have to replace this a here with this product, right? Let me make some space for that first. Okay, I should have done that earlier. Yeah. So instead of this, you will have to say sigma j equal to 1 to L alpha j phi of xj, right? But remember, you cannot, this is again not what you want, right? What you want is to be able to represent this inner product using this kernel functions only, right? So what will this simplify to? Inner product of sigma alpha j phi of xj with phi of, okay, this is also j. So let me, instead of this, let me just change it to xi. Sorry for the confusion. xi, right? So what I want, this is xi, but I will compute this in this form, phi of xj, phi of xi, which I can actually compute as sigma over alpha j k of xj xi. Okay, so that is what I am going to replace this two things with, right? Yeah, this is actually correct. Greater than, and they were the same, but I'll have sigma j equal to 1 to L alpha j kernel applied to xj xi. Same thing here. K xj xi. Okay. So this is my output. Okay. So now if you forget the margin note for a moment, you will see that this right hand side is entirely independent of phi. There is no phi here. You only talk about the kernel function. Okay. Now again, since we cannot have this a here, right? We are not going to have this a here. Instead, we are going to have this alpha vector, which is alpha 1 all the way up to alpha L, so that a can be indirectly calculated from alphas using this, and this we initialize to the all zero vector. Okay, now what do we do? For each, we repeat until there is no update to the alpha vector. What do we do? For each point xj in G, we try to compute this, right? So, but yeah, I should have used xi, but there is too many places in xj. So instead of this, I'll use the summation of a to be over i's, right? So this I cannot uh, compute directly because I do not have an a, but I know how to compute this as sigma. In this case, okay, the summation index has changed. I equal to 1 to n alpha I kernel of a was xi xj. Same thing here, right? Compare this. This is what the same expression that we are having here. You copy this also down here, right? So instead of this, you will have sigma I equal to 1 to L alpha I k of xi xj. This is when you will make an update, okay? When this is your condition, right? This new star, okay? Whenever the star is violated, you make an update. But again, you cannot make an update on A. You just have to store these updates in alpha, right? So here, what does it mean? It means your xj, the phi of xj got added to your A, right? So this you can actually encode by just writing alpha j is equal to alpha j plus 1, right? And similarly, this update you can encode as alpha j is equal to alpha j minus 1. So this would be, since it's a bad point, it will keep on going negative. How many times it will go negative? As many times as phi xj would have been subtracted from A, right? So once you do that, you can ignore the black lines, right? Now that's all. Now the algorithm is the same as above, right? You just have to now kind of, copy it down neatly. Delete everything else, and you see that in the algorithm, the whole of the algorithm, phi is never used. All that is used is k, right? And k will only depend on it will depend only on the small n. Its computation time generally will only depend on small n. But remember, every inner product now there is a summation that runs from I equal to 1 to L. Okay, so there's a trade-off. You don't have a dependency on capital N, the dimension in which you are embedding, but you still have a dependency on this little l, which is the number of points in your data set. Okay, so there is still a dependency on the number of points in the data set. So maybe in some cases that may be too much, in which case we wouldn't use it. But usually these are used on a very small subset of data, and then if the data is small, then you can use this kernel trick, and you do not have to care about what is the dimension in which you have embedded it, right? Okay. Now, yeah, I think it's a good time to stop, but I would rather mention that now at least in the machine learning literature, people would generally ignore phi, right? They'll just ignore phi and only talk about k. Only consider this function k, right? But remember that whenever you are talking about some arbitrary function k, this technique will, at least theoretically, this technique will work only if this k can be written as in this form, right? It will only work if let me to be more precise, there exists a phi from r small n to r capital N such that k of x comma y is actually inner product of phi x and phi y. Okay, so there are ways to linear algebraic and when it is infinite dimensional function theoretic ways to check it. They are called Mercer's conditions, right? But usually you don't have to kind of worry too much, because there are some standard kernels which people use, right? In fact, one of the very common kernel to use is 1 plus inner product xy to the power some d of your choice, right? This is one common kernel to use. You can actually, it's a good exercise to verify that these are indeed kernels. Then you also have this famous Gaussian kernel, right, which is something like norm of x minus y the whole squared with some constant, right? This here actually, to show that this is a kernel, you will have to go into your phi will turn out to be an infinite dimensional embedding, interestingly, right? But there are popular kernels like this, all of which satisfy this requirement here. and you can use this to run this algorithm, right? By the way, this algorithm is called the kernel perceptron algorithm. Okay, this is called the kernel perceptron algorithm, and its convergence condition is the same if under, in whatever is this embedding that is hidden under this kernel operator, if the resulting good set and bad set after that embedding is linearly separable, your algorithm will converge, right? In fact, finally you will end up choosing an embedding for which the kernel is very simple to compute, right? So for example, you remember the standard example that we said, right? Phi of x, we embedded it as some 1x x squared, etc., x to the power d, in which case your kernel turned out to be I think 1 minus xy to the power d plus 1 by 1 minus xy, right? We can actually achieve whatever this phi x does by a simpler kernel, right? So here usually I'll kind of do it in the reverse to see how it is usually done. So suppose we want a similar kernel but which is slightly simpler in terms of, like, let's say floating point computation and so on. If you want something like 1 plus xy to the power d, right? Then what phi will you choose, right? So this is the question, right? What is phi? So you expand this k and c by binomial theorem, you will see 1 plus d choose 1 xy plus d choose 2 x squared y squared all the way up to d choose d x power d y power d, right? This is what it will expand to. But now you can see that if you choose your phi to be this, right? Then if you take your inner product of phi of x with phi of y, you will see that you are getting k of x comma y. Okay, so usually you kind of choose your embedding which gives the simplest kernel function, right? It really doesn't matter how complicated the embedding function actually is. So this phi here and this phi here essentially are equivalent in the sense that whatever is a wherever you get a hyperplane here, you will also get a hyperplane here and vice versa. Only thing is that the coefficients may have to be scaled a bit differently. Okay, so yeah, this is the kernel trick. This is another way of extending your notion of linear separators in a very clever way to find nonlinear separators, like nonlinear separators of various kinds, right? This is the kernel trick. Okay, so I think, yeah, that's we'll wind it up for today. Thank you.